Hello, this is an interview with the authors of the paper on active dendrites. Now, if you haven't seen it, I've made a comprehensive paper review video on this paper, and I released that yesterday if you watch this video as it comes out, which obviously you do. Today, I'm going to interview the authors, and we've all seen my review, so we'll be able to directly dive in. So if you haven't seen the review yet and you want to know what's in the paper, maybe that is a good place to start. The authors here were really helpful and really informative, answering all of my questions and concerns that I had, and even bringing up some new interesting insights. So I hope you learn something from this interview, or at least that it entertains you. And if you have any comments, please let me know in the comments below the video. I'll see you around. Bye-bye. Hey there, today's sponsor is the course on Introduction to Graph Neural Networks. This is a course by my friend Zach Jost, who is an expert in graph neural networks and also runs the Welcome AI Overlords YouTube channel, has a very interesting blog, and does many other cool things. He's packed all his knowledge of graph neural networks into one course that will educate you on both the theoretical and hands-on practical aspect on graph neural networks. Graph neural networks are really important. They're definitely one of the most interesting areas in deep learning right now. They're on the upswing. They model data that has an underlying structure that is connected, that is not really well fit for any of the classic formats like tables or images. They've also powered a lot of recent advances in scientific breakthroughs, such as AlphaFold protein structure predictions or better traffic predictions. So if you're interested in graph neural network, I'll definitely recommend you check out that course. If you use my link, you'll get a 15% discount on the course. Enrollment is open right now and lasts until April 1st or until spaces run out. The course is a 6 weeks course. It's cohort based. You'll get access to a community, to Discord community of other students, and you'll get all the materials and hands-on experience. All right, let's get into the video now. See ya. Hi everyone, today I'm here with the three joint first authors of the paper on active dendrites, Abhi, Karan, and Akash. And I'm very, very happy to have you all here. This paper covers many areas. It covers biology, it covers neural networks, it covers kind of different architectures of stuff. So it's very cool that you all sort of are here and are able to sort of answer my questions. Welcome, all of you.
Yeah, thanks, Yannick.
Thanks for having us.
Thanks for having us.
It's a very interesting paper. So I saw this paper and I was intrigued because it's not often that a lot of people say they do biologically inspired things, but it's not often that someone really goes and says, look, here's what's missing, let's build it in, and then it actually leads to something that works, and that is the hypothesis in your paper, the hypotheses you pose on what should happen are actually confirmed at the end. And this is, I think, a very good story arc for a paper and a really nice thing to write up. So how did this come to be? How did you get the idea of bringing these very not too distant, but these two distant fields together of sort of neurobiology and deep learning?
Well, at Numenta, one of the things we're interested in is in continual learning and learning multiple tasks, more generally speaking. And so, but a lot of neural networks and deep learning today focuses on trying to solve a single task. So we said, well, how is biology enabling the ability to solve multiple things in sequence or, at the same time, learning different things. And so, there's been a lot of work out there on active dendrites. And so, and it's not exactly clear what their role was. But a little while back, we speculated that, hey, they might actually be helping, at the neural level to allow for continual learning. And so if we can build this idea into deep learning, then there might be some prospect there for addressing problems like continual learning and multitask learning.
So is it fair to say that it grew out of sort of a need to solve a task?
I think it grew out of the need to solve multiple tasks in sequence, either learning them together or in sequence continuously. To add on to what Karan was saying is that we believe that active dendrites can really aid in achieving these specialized neural circuits, and we can apply these ideas directly to any neural network and show some competitive performance on various benchmarks that involve continual learning setups. So I guess the purpose of this project, if you were to just summarize it very briefly, is we just want to show a proof of concept for a new idea that can allow deep learning to work in more dynamic environments and scenarios.
To kind of add on to what Karan and Abhi said, so at a higher level, I think we were kind of examining where a lot of modern deep networks fail, and that's in these like streaming task settings and multitask settings. And the kind of like inspiration for our solution was directed towards biology and biological neurons, which is a lot of what Numentus focuses on. And I think quite nicely, we found these like, there are existing benchmarks and existing tasks that show that typical deep learning networks fail in these scenarios. And we were able to build in these like biologically inspired neurons to improve the performance in such dynamic settings by using the fact that we believe active dendrites in biology kind of do this kind of context dependent adaptation in multiple tasks.
What I found interesting is that even though you targeted a little bit towards multi-layer perceptrons, in principle, this active dendrites architecture is sort of pluggable almost anywhere. So you could always imagine some sort of a context-dependent signal that gets routed in and modulates the signal that exists. So I think what I'm trying to find out is there are a number of things happening in this model. There is, first of all, the modulation itself, which is it's not really a known concept, at least in classical deep learning. We always have weighted sums. We rarely have the situation where two parts of the signal are multiplied together, or one modulates the other. It happens a little bit in LSTMs and so on. The other one is this sort of recognition of a context and being context dependent. And then a third thing is this sparsity. Now, you have sort of combined all of them. Is there one thing that you think is specifically important, or is it sort of the combination of things that is really what makes the difference? You have some ablations in the paper. What can you say about this?
I think it's the combination of all these things acting together. So it's the dendrites which are up modulating and down modulating certain neurons to determine which ones should become to determine which subnetwork should be invoked, and then it's the sparsity on top of that, which is ensuring that a large portion of the network is essentially not performing or learning a certain task. And it's those two things together which really gets at this idea of using specialized subnetworks for different things. So I wouldn't say it's any one thing that stands out more than the others.
So when let's get into the paper itself. You've seen my review of it. With respect to just framing the problem and maybe framing the architecture as such, do you think I have captured what you've tried to say? Do you think I've left something important out, or have put emphasis on, or have not put emphasis on something that you would like to put emphasis on when it comes to like what the architecture is, what it does, and how it works?
I think your explanations for the architecture, at least, were very good. I think it definitely does capture what we were trying to say. And the whole point, to kind of reiterate, is that the same model with the same principles should work on completely separate areas. One is the multitask reinforcement learning. The other one is continual learning with permuted MNIST. And I think you touched upon that idea too. So, yeah.
I think that the kind of motivation that I think you in towards the beginning of your review, you kind of compared the typical weighted linear sum neuron with the active dendrites neuron. And I think our motivation in coming up with this architecture was how can we incorporate a lot of these properties into active dendrites with having like dendritic segments being able to either like up modulate or down modulate certain neurons in a way that didn't like completely change from like normal back propagation trainable networks. So like this architecture kind of brings in that flavor of having dendrites influence certain neurons, but does so in a way that mathematically allows for back propagation to train the networks. And I think you touched on that pretty well as well.
Do you think it's valid to sort of bring in biological concepts even though we train with backpropagation? Because, you know, it's very evident that at least pure like correct backpropagation isn't happening in the brain. Do you think, you know, it's still valid to bring in the concepts and maybe the brain's doing something like backprop, or do you think we're sort of just kind of taking inspiration from biology in order to solve some of our problems?
I think it's more so the latter. Of course, the most accurate biological neural network would likely not use backpropagation, right? But this is one area where I think the goal was, can we make deep learning just a little bit more plausible? And in doing so, can we make it a little bit more dynamic? So we're not necessarily here to remove backprop entirely. And say that that's the best way that the dendrites in this architecture can work. Although certainly that is how it works in biology. The point was, can we just augment traditional deep neural nets to work in more dynamic scenarios?
Now, I had some criticisms with respect to just like that details of your architecture. For example, you often choose the number of dendritic segments to match the number of tasks that you have, which obviously, if I was a researcher, I would do the same. But can you say maybe something about how this is in the brain? Like what numbers are we talking about? How many of these sub networks that are composed of distal, you know, dendrites? How many are there approximately? Do you know? Do you have an idea? And, you know, what can you say about, you know, how many we should build into a problem where we maybe don't know how many tasks we expect?
There are, from what I recall, probably in the order of hundreds or thousands of individual dendrite segments for each individual neuron. Actually, it might even be more than that. The actual numbers escape me. But regarding what you said earlier about you know, having the number of tasks be equal to the number of segments here, we found that actually, even though in a lot of the experiments we report here, we do set the number of dendrites to the number of tasks, we found that, you know, we actually don't need to have that many. And we actually have further studies which show that, you know, we can actually keep the architecture fixed and increase the number of tasks we're doing. I'm talking about continual learning here, because for multitask, we're focused on 10 specifically. We can increase the number of tasks, and yet the performance actually doesn't change by much. So that shows that, you know, as we're increasing the number of dendrite segments, we actually end up over parameterizing the network quite a bit, which we don't need to do.
Yeah. So this is the plot on the left right here. You just increase the number of dendritic segments, and the top line is learning 10 tasks, and it doesn't get noticeably worse, which I find to be a very cool property, right? Like, I don't want to have to set a parameter very specifically. I can just, you know, set it too high and it doesn't hurt, which is cool. Which leads me to the plot on the right, where you discuss, you know, the sparsity. I'm going to guess that's the sparsity parameter, so that's the thing that ultimately controls K, right? And I find it peculiar, not that there is an optimal setting, which I would expect, because that I can't set high, that I have to set between like 0 and 1, right? So there's going to be like some optimum in between. But there's this like two bump thing going on. So what's going on there? Why is it like really good at like high sparsity, and then there's like this plateau, and then it just flat, like, crashes down?
I think there in the beginning, if you have too much, I always think in terms of sparsity, so I'm converting from density to sparsity. So if it's too sparse, right, there's not enough signal going through, and that's why as you increase the amount of signal that you're allowing through, as you're increasing the capacity of your representation, then you're going to get an increase in performance. But then if you're using up too many units to create that representation, then you're going to get more interference. Right. And as you have more interference, you're gonna forget more network parameters are overwritten as you move on to subsequent tasks, and so you get a drop in accuracy. And towards the end, you notice that it does fall drastically. Honestly, I haven't thought too much about why that happens, although it is a pretty monotonic fall. Even though I guess in that upper curve there is a slight bump, and that could just be due to seeding or something like that, but yeah,
I was more referring to like the plateau itself, right? There's this plateau kind of, and I know that there could be almost like two modes of using the sparsity. In one mode I have entire subnetworks that do the job, and in the other mode I have like a shared network, yet I have like separate things that just kind of like track which task I'm on, which would sort of correspond to what the baseline is doing, right? When people say, well, the baseline has access to the task too, it can just allocate some units. It's maybe not a perfect analogy, but I was just wondering, it was just interesting to see that there's this type of plateau.
That's something I guess we haven't gone too deep into, but this might just be a property of sparse representations and how much overlap there is as you increase the sparsity level. It could just be something to do with that.
Mm-hmm. So in your paper, you make really, which I appreciate, you make really sure that you sort of always have the same amount of, let's say, trainable parameters in your architectures, and you show that by arranging them correctly, you can achieve a better result. You always use this name of non-zero parameters, right? Is there a difference? Are there large swaths of zero parameters in one of these architectures?
Yeah, so this is something that we control for in the beginning. This is why we mentioned the idea of weight sparsity. So in the beginning, when we're actually creating the architecture from scratch, we decide that some layers have an X% sparsity level applied to it. And what that really means is that X% of the parameters are zero throughout the entire part of training, and even towards the end. So that's why we express everything in non-zero parameters. So the MLPs, for instance, at least in reinforcement learning, are trained with no weight sparsity. So it's completely dense. There are no zeros anywhere in the layers.
And then your architecture, you sort of modulate the amount of sparsity, and that is on top of modulating the K parameter of the K winner takes all layers.
Yeah, there's two aspects to the sparsity. So one is activation sparsity, which is like at a hidden, like when you have a hidden state vector, how many neurons remain non-zero after the activation is applied, which is a K winner activation. And then the second aspect of sparsity is weight sparsity, which is how connected are subsequent layers in the network. So if a lot of the units in the weight matrix are zero, then this models the fact that subsequent layers in the network are not very connected, they're sparsely connected.
To I guess answer your question again on that is it's not something weight sparsity, at least, is something that it's not something we modulate. It's fixed. It's a fixed percentage that we find, and this can either be done through fine tuning or just experimentation.
Okay, because I think I might have just overread that, but I recall that in the introduction you say, both the weights and the activations are sparse, but then sort of I think the winner takes all really focuses on the activations itself. Have you experimented with setting something else than K to a number or a percentage, setting maybe a threshold for sparsity or something like this, where whenever a signal is strong enough, it is let through?
we haven't done anything like that. But we could do that, and there is a chance that it could work out pretty well if we have a fixed threshold. But one potential downside there is that if you have too many signals that cross the threshold, or too many units whose activation crosses the threshold, you're going to get more interference when you train. Or if you have not enough neurons whose activation crosses the threshold, you're going to get that phenomenon which you're showing on the screen right now on the left side, where you have a drop in accuracy because your representations don't have enough capacity. So that's why we opted to go for a fixed value of k. But even if we did have a threshold, I think one of your critiques were here. Now we have another hyperparameter k that we're choosing. In the other case, I mean, our hyperparameter
Yes.
would just be the threshold value there, right?
Obviously, yeah.
Yeah.
So to me, this continual learning setup is very cool, and you can generate data very easily using this permuted MNIST. But there is a bit of an issue that I have, and that is that if I use permuted MNIST, there is another thing. There's like all the tasks are like the same difficulty, right? They're essentially the same task. It's just permuted. So I need to learn like a different function. So this would be the permutation identity, and then the pixels are permuted somehow, right? So all the tasks are kind of the same, right? Which warrants a static network architecture, and every context vector is kind of the same length, right? And all the dendrites, they can sort of specialize in each of their little task recognition. What would change here? Or is this a drastic requirement to your architecture? Or do you think if many of the tasks were wildly different from each other? And you have this a little bit in the robot example. So what can you tell about when tasks are very different in their difficulty, maybe in their amount of training data? Like, how do these things influence an architecture that's targeted towards continual learning?
In our case, I think there might actually be similarities between different tasks. And so, like, for example, in this case, in permuted MNIST, right, there's a certain pixels are more likely to be white, and certain pixels are more likely to be black, depending on the permutation. So maybe two different permutations could have more overlap in terms of which pixels are white, which pixels are black, or they could be totally separate. And if they're more similar, if the permutations are more similar, then we could expect that the subnetworks that are selected by the dendrites will probably are likely to overlap more in which neurons become active, since there's probably a lot of similar computation going on. But of course, in that case, difficulty doesn't really change at all.
I think to add on to that, I think a lot of it depends on the quality of the context signal, because ultimately that's the part of the network that indicates to the active dendrites what kind of task you're solving, how similar is it to previous tasks you might have seen, and things like that. So I think that in this permuted MNIST case, the way we're computing the context does allow for this property that Karan just mentioned, where if there's some overlap in the input space, then the context signal for that will demonstrate this input and perhaps allow for overlapping subnetworks to emerge. Whereas if you have like wildly different tasks, which is something we see more in the robotics environment, then these context signals can like differ more and indicate that the subnetworks must not overlap. I think it would be really interesting, and we've talked about this before, to try a similar setup in a continual like robotics learning case where you have a streaming set of like robotics tasks. And I think that would probably be a super interesting study to do, and something that hopefully we will try at some point in the future.
So I had some observations with respect to your experimental setup. And it's very cool that you do two different things, but there are also noticeable differences on how you implement the two different tasks, right? In the first task, you give the task ID directly. In the second tasks, you do this prototyping approach, which is a more advanced approach. Can you tell a little bit about is there like a reason why because I could also imagine you just give me the task ID in the second task, or I do the prototyping in the first task. Is there like a research process reason? Like, did you find that some things did work or didn't work, or how did this come about that all of a sudden we're introduced in the new task, we're introduced to this new way of detecting the context?
I think in the context of the multitask reinforcement setup, like the environment setup itself gives the task ID. And I think that the concept of multitask learning itself is more focused on if you have different tasks which may conflict with one another in terms of the types of behavior you have to do or the types of predictions, how can you mathematically still optimize your like joint objective function without and still be able to perform well on all of the tasks? And the problem shifts not so much from trying to infer what task you're doing to more, what task you're doing and you want to try to do all of them. How can we like optimize this joint objective? And this is kind of the way we use this one-hot task encoding is in line with past works that deal with multitask learning and multitask reinforcement learning, where you have this like one-hot task encoding that is provided. I do agree that like the one-hot encoding is quite convenient and a little bit arbitrary. You can probably use like a denser representation for each task or try to infer it. But I think for the purposes of our experiments, this one-hot encoding seemed simple as it was environment provided, and kind of like the point of the multitask setup was to, again, like try to show that this network architecture prevents from like conflicting updates across tasks and avoids this like interfering updates from occurring. I think for continual learning, the kind of setup of the problem itself is a little bit vaguer in that you're not always provided with the task IDs and you have to infer this on the fly, which again, I think Karan can talk a little bit more about.
In continual learning, there are a couple other recent papers that have come out in the last couple of years, and they're not providing task ID, and the model actually needs to infer the task ID as it does some sort of modulation or whatever their technique is. So we thought that makes the problem a bit more challenging, a bit more interesting. So since we are working on continual learning and comparing to some of these other methods, let's also try to infer what the task should be.
So it's if I hear this correctly, it's very much inspired by the environment itself, like what the problem is supposed to be, and not like, because if I see something like this, I always have the vague suspicion that people try something and it didn't work, and there's like, well, let's try something else. But there's also, I mean, I don't want to infer that, so it's always good to hear like, okay, this really came about through the environment. And I mean, it would be equally cool if it was the other thing, but I'm just always interested to hear so I can adjust my priors. I think
just to add really quickly, I think in the reinforcement learning setup as well, because the state space is like similar, is shared across all the tasks, because essentially it's hard to infer from the states what task you might be doing if you weren't given such an ID. And the only information you would have is like the reward signal, and that might not be enough to like infer what the task is. So like giving a task ID
given that it's at the end, right?
Yeah,
like, it's like you do something and then you get like a reward, and then you find out what task you just did. Like, that's okay. I agree with you. That's really not helpful at all.
Also, I think one thing to add here is that we did try a couple. So I think this is something you pointed out in your intro, where the task IDs that we're using are one-hot encoded, right? At least for multitask RL. And that means that all these tasks are entirely orthogonal to each other. And it really doesn't reflect how similar one task is to another. And it really doesn't also reflect how different one task might be from another. So one thing that we were experimenting with, I think we mentioned briefly in the paper, is that we tried having an embedding layer that effectively embeds this one-hot encode into some other higher dimensional representation, and using this instead of that one-hot encode as a context. And I think what we eventually found was that using the embedding or not using the embedding produced fairly similar results. So we just decided to remove it for simplicity's sake. But one thing to note is that using the embedding allows you to represent contexts, I think, that are a little bit more nuanced, in the sense that the embedding, since it's trained via end-to-end backprop, any task that is similar to another task would have a shared representation in that higher dimensional embedding, and ones that are really separate from each other would likewise correspond to huge distances apart in that higher dimensional space. But the one-hot encode is entirely orthogonal from each other, each task, but it still worked out pretty well compared to the embedding.
I mean, yeah, and if it gets more complicated, I think you could put entire sub-neural networks, instead of that, even that embedding layer, you could have non-linearities inferring sort of more complicated task embedding or task relations. It is interesting though with respect to the context itself. You learn these things, all of this through backprop. And my question, I think I brought this up, is would this be like a candidate for maybe unsupervised pre-training, that you sort of maybe collect episodes or something in your multitask RL and then just sort of decide based on this, how do we structure our dendritic segments in order to recognize the context, maybe some sort of contrastive objective or anything? Like, is this something that came, I just blurt these things out when I do the reviews, right? I never know if they're entirely stupid or if people have thought about it and discarded it. Is that something that is a candidate?
I don't think it's something that we considered, but an interesting thing to note is that if we did use this for some kind of unsupervised pre-training tactic, is that when you're actually fine-tuning the network, your context vectors are different. So that's something I think that would be the most important nuance to investigate. I personally don't know how well that would work if we trained on a set of contexts that are different during the unsupervised portion, and then use a totally different set of contexts during the fine-tuning procedure. I would imagine that doesn't work well. So yeah.
To add on to that, I think, kind of like when I heard you say that in your review, it was quite interesting. I think from the perspective of reinforcement learning at a high level, I don't know if this will work out, but it would be quite cool to see if you can train these dendritic segments to either produce, like if you can train them to recognize different contexts and maybe guide exploration in different ways based on the context in an unsupervised manner, and maybe like do different things in different contexts as an exploration strategy. I think that'd be super cool. Again, I think the challenge there would be to like come up with a clever way of generating context in an unsupervised way. So I think that would be an interesting area of investigation, as to like how do you come up with context signals in an unsupervised manner. A contrastive approach might be cool there. And given these contexts, how do you train these active dendrites to modulate neurons to do what you want it to do? And I think thinking about that in the lens of exploration in RL could be quite interesting.
Yeah, you could sort of even prepare for contexts that you hadn't considered before. Maybe new instructions in a familiar environment or something like this. You have this notion of prototyping to recognize the context, which I found very interesting because it's sort of it's kind of like an unsupervised online way, even like as the data streams in, you create these new prototypes and so on. And sure, there's some hyperparameters, but I think my main concern is that, just taking the average of the samples as they come in right here, it's going to work for something very simple, like permuted MNIST or so, but this gets to its limits very quickly, right? If I think about ImageNet classification or so, it is quite limited. How can this idea be extended to, let's say, arbitrary complexity? Like, what would I have to do with this online prototyping approach to make it, to make it usable for more complex problems?
Hey, look, I think you're absolutely right that this technique only works for something like permuted MNIST, where you get really good task separation through just averaging the examples from a single task. And that's why it works so well here, right? We actually evaluated how well this clustering procedure works, and it's like it works pretty well. It's not misclassifying things when it's clustering the prototypes. But if we want something that's a bit more general and can apply to other domains like ImageNet, as you mentioned, I think something along the lines of self-supervised learning might help there. That way, you're trying to build a context vector that is going to provide you sufficiently good task separation, and it's not as simple as just averaging. Does that get at your question?
Yeah, no, absolutely.
And I think also in like meta learning literature, there are prototyping methods that maybe like process the raw input into an embedding space and then do clustering similar to what we're doing there. So I think that would be a quite simple approach that is similar in flavor to this one, but kind of embeds the raw input, like an ImageNet input, into some better clusterable space.
Is another thing I noticed, and this is a minor thing, but here you feed the context signal into both of your layers, and in the experiment before here, you draw this very, very accurately. You feed the context signal into only one of the layers, so it doesn't go in here. Is there a particular reason behind the choice of this?
Yeah, so there's a bit of background regarding this. I want to say first that the continual learning and reinforcement learning projects started out as separate areas within Numenta. And the goal for this was really to see if the same principles of the same model could work equally in both of these areas. So while we did modulate both the layers in continual learning, the intuition for not doing so in reinforcement learning was a bit different. It was that the first layer should contain all the shared information the model needs, and you could really do this without activating any specific subnetworks. And that the second layer would then activate the context-dependent subnetworks for each task. But you're absolutely right that we could have tried doing in-depth experiments where we modulated both layers for the RL setup. I think we started doing that at the beginning of this project, but we found it worked reasonably well. But because of the time and computing constraints of running each of these RL experiments, we decided to stick with the original plan and really pick a few key experiments and key architectures to run, and really leave the ablations for the continual learning experiments, which are really significantly faster to run. But you are absolutely right, though. We just went off of our intuition on this one.
I mean, I don't want to it's just my reviewer too popping up and be like, hey, but it's good. I mean, it's even interesting to see, that this is kind of a convergence of projects. Could you tell us a little bit more about just the research process? You already talked about how this came to be, but like the process of researching this, it's kind of a new thing, right? You propose a new architecture. The tasks are, let's say, not that mainstream. People work on them, but they're not super mainstream. Was it like smooth sailing from beginning to end, like stepwise improvement, or was there points that just didn't work at all for a long time? Are there entire avenues that you discarded and didn't end up working out? Like, could you, I don't know, let other people, I don't know what you can or want to disclose, but it's always interesting to hear, what also didn't work out during a project.
Yeah, I can start off. When we first tried implementing some of these ideas behind dendrites, you noticed that we talk about this that we're picking the maximum dendritic activation, and then and we're using that to modulate. But actually, it was through the process of trial and error that we realized that we were just working on an initial toy task. We weren't working on continual learning back then. We found that, hey, we actually can't turn things off. We can only turn them on because you are picking the maximum value, right? So how do you get something that's super sparse? So we actually want to turn things off. So he's like, oh, okay, let's go back and let's actually not just pick the maximum, but pick the maximum and keep the sign. So if something's really negative, we're picking that. And so there's a whole appendix section, and that's actually the detail of how that's in the details of how we're actually implementing this. So through a bit of trial and error, and then also with picking going back to the prototype. For a while we were thinking, well, how can we get something that really provides sufficient task differentiation? So we tried a bunch of different things. We just like Abhi mentioned, he had a linear embedding which was created from his context. We also had one for continual learning, but that didn't really work too well either. And we ended up converging on something that's really dumb and simple for permuted MNIST. That ended up working out. Yeah.
There's actually, just based off of what Karan was saying, if you go to figure 11, I think you had some points there as well. It's a visualization, if I remember correctly. Yeah, this one.
11. Yeah.
So if you notice, like we use the exact same gating technique for both continual learning and multitask reinforcement learning, and that's the absolute max gating. So you're picking not only the absolute max, but you're retaining the sign. And what you'll notice is that the initial intuition for doing this was that, as Karan just said, is you want to give each neuron the ability to either turn on or turn off. And it's very interesting because if you look at the results in multitask RL, you can see that for neuron B at least, you see some negative activations, those red squares that you see. So that's effectively the neuron being told to turn off. It's the exact opposite of a strongly positive activation. But I think what's something that's very interesting to see is, at least for the two neurons that we've showed for continual learning on the right-hand side, you don't really see that happening. It's either the neuron doesn't receive high magnitudes of activation, or it receives really high magnitudes, but it's all positive. So it's something interesting to note, that we were even in the multitask RL part, we were trying to understand, would max gating work better than absolute max gating, in the sense that do we want to discard the sign or keep the sign? So yeah, there's a lot of, in the beginning, there was a lot of trial and error process. In multitask RL too, we had a good amount of time spent on understanding what the right sparsity levels were to apply for the weight sparsity in the feed-forward layers. What we saw, I think, is also pretty it's intuitive. If you really increase your sparsity level to a really high sparsity, there's just not enough information in the network to keep training, and your accuracy sort of plummets. But something that's interesting to note is that there's always a sweet spot for sparsity, and once you reach there, that's when the accuracy is the best.
And how do you debug these things? What is your main method? Is your main method mainly setting a parameter and then running things, or what are good ways to are there good ways to peek inside and what's happening? Like, what are things that you look at to debug something like this? Like, oh, we are not sparse enough, or we're too sparse, or we don't turn off neurons, or something like this.
I think diagrams like this, which you have on your screen, are a perfect example. Visualizations of how the dendrites are behaving. So I think there was at one point early on, here you have in both cases, after learning that different segments are responding to different tasks contexts. But there are cases where this early on where these diagrams looked exactly like just horizontal bars, right? So you have the same segment that's just winning all the time. And so we realized, okay, well, this is not right. We don't want the same segment to always win. So that helps in identifying, okay, this is why the network is failing. And so we go back.
So you would look at these things even during your research process. It's not just something that you made after the fact, just to demonstrate to the readers.
Yeah. Oh yeah. Yeah. This was a very helpful tool for debugging.
Cool. I mean, that's really interesting to hear, right?
And a lot of the architecture decisions that were made in continual learning were used in multitask RL, simply because I think each multitask experiment took 25 hours to run plus easily. So it was really hard to change a parameter, observe how the results and visualizations looked, and then sort of edit it from there on. So a lot of the intuitions that we got in RL came from Karan's continual learning experiments. So that was nice.
Did you ever compare these things to, well, it's not too easy to compare, but sort of a baseline, because there is the danger with these things that you kind of interpret. I think I said, well, couldn't this be just like the difference between the top and the bottom just be, one is at initialization and one is trained and maybe has not much to do with sparsity? Did you ever compare this to something that isn't explicitly sparse or anything like this? Like, is there something you can say as a reference point?
Yeah, so there's two things to note there. The first is that, at least for this visualization, the activations are normalized with respect to when they were trained. So I think you mentioned this in your intro as well. You said that could it potentially be that you have really high activations in the beginning, and the area that you've circled there in purple, it just sort of gets dimmed down. And I think the important thing to note is they're all normalized. So the range of values between the highest activated neurons are much higher than the lowest activated neurons after training than before training. But to address the second point, I think that's regarding figure 10, if you scroll up. And that was, why don't we have like a baseline for this? Is it really that the active dendrites networks that are creating these hypersparse subnetworks? And to that, you're absolutely right. We should have had a nice diagram here that also showed how this would look in a baseline MLP. You're absolutely right. That's something that we could definitely include.
I mean, I totally believe you that it's like very sparse. It's just that it's not obvious from a diagram like this. Like what should I expect? Yeah, but cool. Yeah, there is one other thing in that. By the way, like I have mad respect for you for including the graph on the right. Like mad respect. Like 90% plus of researchers where they try something like this specifically because no one would notice if you leave this away, right? No one comes to you and says, well, okay, maybe someone comes to you, but no one would seriously miss adding the SI to both of these things. And you know, at the left, you beat them very clearly. So, you know, huge respect for including that. That is, it's I think to be commended and to be highlighted.
I think you know, when we present a new architecture like this, you know, we really want to show the community that, hey, we can do things like continual learning with our more biologically inspired ideas. And it's competitive with what's already out there, right? So even if we're not beating the state of the art, I think that's perfectly fine. Even though, you know, nowadays a lot of machine learning has turned into this competition of, you know, getting the best numbers, and if you don't have the best numbers, apparently that means you won't be able to publish anymore. So
yeah, to add on to that, I think the purpose of this paper was really something I said that we all said in the beginning, and now it's we really want to show a proof of concept for this completely novel architecture, where the goal is really not to get state-of-the-art accuracy on either of these benchmarks. It's really about the promise of something new, something that I think that deep learning has been missing for the past, 10 years or so. So yeah, it's exciting.
And the last thing maybe we can get into is this comparison to other networks, because you very clearly address this in like a paragraph, and I think I have like even a transformer diagram somewhere. You clearly address this in a paragraph saying like, isn't this just equivalent to like a bigger network? And I try to myself also to come up with, you know, is there some way I could do the multiplication in like an MLP? And I'm fairly convinced there isn't, but there is a connection clearly to like LSTMs, which do modulate things with like forget gates and so on. They even have sigmoids, right? So they can model this on or off, and also sparsity to an extent. And I also think that a transformer could conceivably, like a two-layer transformer could conceivably model the interaction right here. Did you explore at all like the connections of sort of this active dendrites framework to other models? Is there something you can say about that?
I definitely think that these are great observations, by the way, that the kind of relationship between attention and transformers and like the gating and LSTMs and GRUs, there's definitely a relationship between those mechanisms and what we're doing here. I think in our research process, we definitely thought a lot about how this gating mechanism could be related to like things like multi-headed attention, where basically you're doing a similar thing where you're matching keys and queries as vectors with an inner product, and then using that as a way to see what parts of a sequence, for example, to wait when you're considering a certain position. I think the key difference in terms of, I think the similarity is that for in the specific instance of attention, you are using learned weights to match a given input. So, for example, in our active dendrites, you're matching the context with the set of dendritic segments, and in attention, you're matching like the query vector with a set of keys. I think that the key difference is that the purpose for which it's done. Here in active dendrites, you're looking at a specific neuron and you're saying, okay, given the context, is this neuron relevant? In transformers, you're saying, okay, here's a position. What context around me in terms of the sentence, for example, is relevant for me? and how can I weight certain aspects of it. So I think it's a little bit like flipped in how in the interpretation of the focus. Kind of shifting to the LSTM aspect, I think as a mechanism, it's quite similar in that the LSTMs actually like turn off or turn on certain units themselves to carry forward in time. I think, yeah, exactly. That's what's done here. I think that the difference is now like focused more on the sparsity aspect of it. In LSTMs, you're doing like a weighted sum between what's in the past and what's current, and saying, okay, let's pass this forward. And there's no aspect of like using this to enforce a level of sparsity. Here we're saying, okay, like let's turn off certain things and do that in order to remain sparse and pass forward this information. So there's definitely a relationship there. I think the interpretation is similar but a little bit different.
And I think in all of these things, again, to highlight, LSTMs and transformers, they're all trained, let's say, with backprop, and all the parameters are trained. So still, you'd run into the same problems where if you do this continual learning, tasks would interfere with each other, no matter how much they can implement the multiplication. So that's definitely a difference. So in your Outlook section, I haven't mentioned this in the video, but you discuss sort of what to do next, and you mentioned a lot of like, oh yeah, we want to investigate maybe the combination of RL and continual learning and so on. Is there something that's here? Is there? Yeah, you said you mentioned neuroscience a little bit. What would be sort of the next big things from neuroscience to include in deep learning architectures that aren't yet really done by other people? Like, is there something where you could say, well, if we had that, that's not really in our deep networks yet, but if we had that, that would be like amazing.
I think this is a very small point, but the dendrites that we're sort of modeling right now they can be considered the basal dendrites. I think you went over this briefly in your intro, and the basal dendrites are responsible for receiving this context and depolarizing the main cell to either fire or not if that context was recognized. Something that we haven't looked into, which could be potentially interesting, is modeling apical dendrites. And the apical dendrites receive feedback either from they receive feedback from other cells, and that also biases the soma to fire or not. I think that could be a potentially interesting way to also gate each individual neuron. I think standard deep learning doesn't do any of this anyway. They only consider the proximal dendrites, which is mimicked by this simple linear weighted sum to determine if the neuron is fired. But if we can gather all this other neuroscience background from all the other kinds of dendrites too, like apical dendrites, it could be a very potentially interesting architecture, like a very powerful one for dynamic scenarios.
I mean, the issue of top-down feedback or lateral inhibition or anything like this, it's a lot of people talk about it, but I haven't yet seen anyone successfully sort of bring it into a deep network and actually do something useful with it. So yeah, definitely think, beyond dendrites, just mechanisms like this would be super helpful.
And I think like another aspect, which is a little bit quite different from what Abhi just said, that would be quite interesting, is the kind of local learning rule aspects that are present in biological neurons and how they might relate to unsupervised learning in traditional machine learning. I think a lot of the unsupervised learning objectives are kind of addendums to the loss function that we think might be useful, and it just kind of flows through the network. And kind of, I might be wrong, but I don't think there's a lot of research into like figuring out which parts of the network could focus on certain things in an unsupervised way, which might be better done in biological networks. So I think thinking about that and getting inspiration to see like what kind of local learning rules in an unsupervised way could improve performance in modern deep learning would be super cool.
Cool. Yeah. So, do you have anything to add? Anything people should know or that we haven't talked about yet about the paper? People can get started with your code, which is online, right? I've seen that, which is very cool. Yeah. Anything you want to get out there to the viewers?
the take-home message from this is what we want to be is that look, the brain is able to do a lot of different things. It's using different neural circuits to do it, but neural networks, as they've been designed decades ago, they're really just optimizing for one thing. They're great function approximators, but you don't just want to approximate one function. You want to be able to approximate multiple functions. And so we're trying to show that, hey, look, there are ways where we can get neural networks to actually, have different sub networks, different neural circuits that are able to be independent, be different function approximators. And if we can do that, then neural networks will be able to operate in more dynamic, changing scenarios. And I think that's really exciting because the world is constantly changing. But a lot of the applications for deep learning right now are a lot of the environments that they operate in are static. So if we can get to that, then that's great.
Cool. Well, Akash, Karan, Abhi, thank you very much for being here today. This was great fun, and I learned a lot.
Yeah, thanks, Yannick. And now you're influencing my fashion.
Nice.
I'll join the show.
Thanks so much for being here. I hope you continue this because it's really cool, and I think we're missing it in deep learning.
Thanks, Yannick. That was a lot of fun.
It was a pleasure.
Thanks for having us.